Imagine standing perfectly still while the entire universe around you rushes forward through time. Not metaphorically, but as a physical reality, measurable with precision instruments. Now imagine that same effect amplified to such extremes that years, decades, even centuries could pass in the wider universe while only moments tick by for you. This isn't science fiction. This is what happens near a black hole, and it's one of the most profoundly verified predictions in all of physics. Time itself bends under gravity, and tonight, we're going to understand exactly how we know this, why it happens, and what the measurements actually tell us. If you're curious about the universe and how reality works at its most extreme edges, stay with me through this exploration. And if you find this fascinating, consider liking this video and subscribing so we can continue discovering the universe together. Now, let's begin at the beginning, with a seemingly simple question that changed everything. For most of human history, time was considered absolute. A second was a second, whether you measured it on Earth, on the Moon, or anywhere else in the cosmos. Clocks might break or run poorly, but time itself was thought to flow uniformly throughout the universe, like an invisible river carrying everything forward at exactly the same rate. Isaac Newton formalized this view in his laws of motion, treating time as a fixed background against which events occur. This perspective worked remarkably well for describing planetary orbits, falling objects, and essentially all motion we encounter in everyday life. But it was wrong. Not approximately wrong, but fundamentally wrong about the nature of time itself. The first person to recognize this was Albert Einstein, though the path to this recognition was indirect. In 1905, Einstein published his special theory of relativity, which demonstrated that time is not absolute when objects move at high speeds relative to each other. Two observers moving at different velocities will measure time passing at different rates. This was strange enough, but it applied only to motion through space, not to gravity. Einstein knew something deeper was at work. He spent the next decade struggling with a puzzle. If time could be affected by motion, and if gravity felt indistinguishable from acceleration, then perhaps gravity itself affects time. This insight led him to general relativity, published in 1915, which proposed something radical. Gravity is not a force pulling objects together, but rather a curvature of space-time itself. Mass and energy warp the fabric of space and time, and objects follow the curved paths through this warped geometry. What made this revolutionary for our understanding of time is that Einstein's equations predicted something unexpected. The stronger the gravitational field, the slower time flows. Not slower as experienced by someone within that field, but slower as measured by someone outside it. To someone living deep within a gravitational field, their clock ticks normally, their heart beats normally. Every process proceeds exactly as expected. But to an observer far from that field, watching from a region of weaker gravity, those same processes appear slowed down. This phenomenon is called gravitational time dilation, and it emerges directly from the mathematics of general relativity. The equations show that time is not a separate dimension ticking away independently, but is interwoven with space into a four-dimensional spacetime that curves in the presence of mass and energy. When Einstein first published these ideas, they were mathematical predictions without experimental confirmation. The prediction was clear: a clock in a stronger gravitational field should run slower than an identical clock in a weaker field. But the effect is extraordinarily small under normal circumstances. Earth's gravity is far too weak to produce time dilation that anyone could measure with the technology of 1915. Einstein could only wait and hope that someday, somehow, someone would test his prediction. That test came sooner than anyone expected, though not in the way Einstein anticipated. The first experimental confirmation of general relativity came in 1919, but it involved the bending of starlight around the sun during a solar eclipse, not time dilation. For gravitational time dilation specifically, scientists needed clocks accurate enough to detect incredibly tiny differences in time. Such clocks didn't exist in the early 20th century. Mechanical clocks, even the best ones, were far too imprecise. What scientists needed was a natural clock, something in the universe itself that ticked with perfect regularity and could be measured carefully. They found it in atoms. Every atom emits light at specific frequencies determined by the energy levels of its electrons. These frequencies are extraordinarily stable, like a natural metronome built into the structure of matter itself. In 1960, physicists Robert Pound and Glenn Rebka at Harvard University used this property to test gravitational time dilation right here on Earth. They placed a gamma-ray source at the top of a tower about 22 meters tall and a detector at the bottom. The gamma rays emitted from the top had to climb up out of Earth's gravitational field to reach the detector below. Wait, that sounds backwards. Actually, the rays fell down the gravitational field from top to bottom, gaining energy in the process. The experiment measured whether the frequency of the gamma rays changed during this fall, exactly as general relativity predicted. The result was unambiguous. The frequency did change, by exactly the amount Einstein's equations predicted. Time at the bottom of the tower, where gravity is infinitesimally stronger, runs slower than time at the top. The effect was almost incomprehensibly small. Over the 22-meter height difference, the time difference amounted to only a few parts in 1,000 trillion. But it was measurable, and it matched the prediction precisely. This was the first direct experimental confirmation that gravity affects the flow of time. The experiment has been repeated many times since, with increasing precision, and every single measurement confirms the prediction. Gravitational time dilation is not a hypothesis or a theoretical possibility. It is a measured property of reality. As atomic clock technology improved, scientists gained the ability to measure even smaller time differences. By the 1970s, atomic clocks had become accurate enough to detect gravitational time dilation over just a few meters of altitude change. In 1971, physicist Joseph Haffel and astronomer Richard Keating performed a remarkable experiment. They flew 4 atomic clocks around the world on commercial airplanes, 2 flying eastward and 2 westward. When they compared these clocks to identical clocks that remained on the ground, they found measurable differences. The airborne clocks had experienced less gravity because they were at higher altitude, and they had also been moving at high speeds, which introduces time dilation from special relativity as well. The combined effects were small, measured in billionths of a second, but they matched the predictions of relativity within experimental uncertainty. Time genuinely flows at different rates depending on both your altitude in a gravitational field and your velocity through space. Today, gravitational time dilation is not just confirmed but routinely accounted for in practical technology. The Global Positioning System, which relies on satellites orbiting Earth at an altitude of about 20,000 kilometers, must correct for gravitational time dilation to function accurately. The atomic clocks aboard GPS satellites are in a weaker gravitational field than clocks on Earth's surface, so they run faster by about 45 microseconds per day. Simultaneously, because the satellites are moving at high orbital velocities, special relativistic time dilation makes their clocks run slower by about 7 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day compared to ground clocks. This may sound trivial, but GPS determines position by measuring the time it takes for radio signals to travel from satellites to receivers. Radio waves travel at the speed of light, roughly 300 million meters per second. A timing error of 38 microseconds would translate to a position error of about 11 kilometers. Without correcting for both gravitational and velocity-based time dilation, GPS would be essentially useless for navigation. Every time you use GPS to navigate to an address or find a nearby restaurant, you are relying on technology that must account for the fact that time flows at different rates in different gravitational fields. These experiments establish beyond any doubt that gravitational time dilation is real. But they also show us something else. Under ordinary circumstances, even in Earth's gravity, the effect is small. To experience dramatic time dilation, you need much stronger gravity. That brings us to black holes, objects where gravity becomes so extreme that its effects on time become impossible to ignore. A black hole forms when matter becomes compressed into such a small volume that its gravitational field overwhelms all other forces. The most common way this happens is when a massive star exhausts its nuclear fuel and collapses under its own gravity. If the star is massive enough, no known force can stop the collapse. The matter crushes inward, becoming denser and denser, until it forms a region of spacetime so severely warped that nothing, not even light, can escape from within a certain boundary. That boundary is called the event horizon. The event horizon is not a physical surface or barrier. It is simply the point of no return, the distance from the collapsed mass at which the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever come back out. What makes black holes relevant to our discussion is that the gravitational field near a black hole is extraordinarily strong, and therefore the time dilation effects are correspondingly extreme. To understand just how extreme, we need to think about what an observer far from a black hole would see when watching something approach the event horizon. Imagine an astronaut falling toward a black hole while continuously transmitting a radio signal back to a spaceship hovering safely far away. As the astronaut falls closer to the event horizon, they are moving into regions of progressively stronger gravity. From the astronaut's perspective, everything seems normal. Their watch ticks at its usual rate, their heart beats normally, they feel no local change in the flow of time. But to the observers on the distant spaceship, something strange happens. The radio signals coming from the falling astronaut begin to arrive at longer and longer intervals. Each subsequent signal pulse takes more time to reach the ship than the previous one. This is gravitational time dilation at work. The closer the astronaut gets to the event horizon, the more slowly time appears to pass for them from the perspective of the distant observers. The astronaut's clock appears to tick slower and slower. Their movements appear to become more and more sluggish. The wavelength of the radio signal they're transmitting gets stretched, shifting toward lower frequencies, a phenomenon called gravitational redshift. The redshift becomes more extreme as the astronaut approaches the horizon. Mathematically, as the falling astronaut gets arbitrarily close to the event horizon, the time dilation approaches infinity. To the distant observers, the astronaut appears to slow down asymptotically, getting closer and closer to the horizon but never quite reaching it. The light from the astronaut becomes increasingly redshifted, dimmer and dimmer, stretched to longer and longer wavelengths until it fades beyond detectability. From the perspective of the outside universe, the astronaut becomes frozen at the event horizon, eternally suspended at the moment of crossing. This does not mean the astronaut actually stops or hovers at the horizon. From their own perspective, they cross the event horizon in finite time and continue falling inward. But the outside universe never sees this happen. The information about the crossing never reaches external observers because the light carrying that information would have to travel outward from inside the horizon, which is impossible. This leads to a profound observational consequence. From the perspective of the external universe, nothing ever crosses the event horizon of a black hole. Every object that falls toward a black hole appears to slow down and freeze just outside the horizon, gradually fading from view as its light becomes infinitely redshifted. This might seem to contradict the idea that black holes grow by consuming matter, but the resolution lies in understanding what we mean by time. The infalling matter does cross the horizon and does contribute to the black hole's mass. But from the external universe's frame of reference, this happens at the end of infinite time. The external universe and the infalling object have such drastically different experiences of time near the event horizon that they essentially inhabit different temporal realities. The mathematics behind this is precise and comes directly from the Schwarzschild solution to Einstein's field equations, which describes the spacetime geometry around a non-rotating, uncharged black hole. The Schwarzschild metric includes a term that quantifies gravitational time dilation at any distance from the black hole's center. At large distances, time flows almost normally. But as you approach the Schwarzschild radius, which defines the event horizon, that term approaches zero. Time, as measured by distant observers, slows toward a stop. The equations tell us exactly how much time dilation occurs at any given distance from the horizon. For a concrete example, consider a black hole with a mass 10 times that of our Sun, which would have an event horizon radius of about 30 kilometers. If you could somehow hover at a fixed position just 1 kilometer above this event horizon, time for you would pass at about 14% the rate experienced by someone far from the black hole. For every hour that passes on your watch, about 7 hours pass in the distant universe. If you could hover just 100 meters above the horizon, time would slow to about 4%. Your 1 hour corresponds to about 25 hours far away. At 10 meters above, you'd experience about 1% of normal time flow. Your hour equals about 4 days in the distant universe. The closer you get, the more extreme the effect becomes, approaching infinite dilation exactly at the horizon itself. It's crucial to understand that this slowing of time is not an illusion or a trick of perception. It's not due to delays in light travel time, though light travel does introduce additional complexities. The time dilation is a fundamental aspect of the geometry of spacetime itself. An observer hovering near the event horizon genuinely experiences less proper time than an observer far away. If you could somehow survive hovering just above a black hole's event horizon for what feels like a few hours to you, then escape back to distant space, you would find that years or even decades had passed for everyone else. This is not because your watch broke, or because you traveled through space, but because the spacetime you were inhabiting was so severely curved that time itself flowed more slowly. This raises an interesting question. We've established that time slows near black holes as measured by distant observers, but what about for someone actually falling in? From their perspective, do they experience slow time? The answer is no. A person falling freely into a black hole experiences time passing normally by their own measurements. Their watch ticks at 1 second per second, their thoughts proceed at normal speed, their heart beats normally. This is a fundamental principle of general relativity called the equivalence principle. An observer in free fall doesn't feel gravity. They are in an inertial reference frame, and all their local measurements of time and space come out perfectly normal. The extreme time dilation is only apparent when comparing their clock to clocks far from the black hole. This might seem contradictory. How can time be both normal and dilated simultaneously? The resolution is that time dilation is not an absolute property but a relational one. It describes how different observers in different gravitational fields measure each other's clocks. There is no universal, absolute time flow that we can compare everything against. Each observer has their own proper time, the time measured by a clock they carry with them. These proper times are all equally real and equally valid. The disagreement between them is not a measurement error but a genuine feature of how time works in curved spacetime. The extreme gravitational fields near black holes also produce other measurable effects beyond simple time dilation. One is gravitational redshift, which we mentioned briefly earlier. Light climbing out of a gravitational field loses energy, which manifests as a shift toward longer wavelengths, toward the red end of the spectrum. For light emitted just above a black hole's event horizon, this redshift becomes extreme. The light stretches to longer and longer wavelengths, losing energy as it climbs out of the gravitational well. By the time it reaches a distant observer, light that was emitted as visible light might arrive as radio waves, or even lower energy radiation. At the event horizon itself, the redshift becomes infinite. Light emitted exactly at the horizon would need infinite energy to escape, which is another way of understanding why nothing can escape from within the horizon. Astronomers have observed gravitational redshift from light emitted near black holes in binary star systems. When a black hole is paired with a normal star, it can pull matter away from that star. This matter doesn't fall directly into the black hole but instead spirals around it in an accretion disk, a swirling disk of superheated gas. The inner regions of this disk orbit very close to the event horizon, in regions of extreme gravity. Light emitted from these inner regions shows significant gravitational redshift, exactly as predicted by general relativity. By measuring this redshift, astronomers can determine how close the emitting material is to the event horizon and thereby confirm the presence of a black hole and measure its properties. Another observable consequence of extreme gravitational time dilation appears in the behavior of matter falling into black holes. When matter in an accretion disk spirals inward, it heats up due to friction and compression, eventually becoming hot enough to emit X-rays. These X-rays escape from the disk and can be detected by X-ray telescopes orbiting Earth. However, X-rays emitted from the innermost regions of the accretion disk, very close to the event horizon, experience extreme gravitational time dilation and redshift. An X-ray photon emitted from deep in the gravitational well arrives at Earth stretched to lower energy and frequency. Detailed observations of X-ray emissions from black hole accretion disks show exactly this pattern. The spectral lines in the X-ray emission are broadened and shifted in ways that match the predictions of general relativity for emission from regions of strong gravity. These observations provide strong evidence that the time dilation effects predicted by Einstein's equations actually occur in nature around real black holes. Perhaps the most dramatic confirmation of extreme gravitational effects near black holes came in 2019 with the first direct image of a black hole's shadow. The Event Horizon Telescope, a global network of radio telescopes working together, captured an image of the supermassive black hole at the center of the galaxy M87. This black hole has a mass about 6.5 billion times that of our Sun. The image shows a bright ring of emission surrounding a dark central region. That dark region is not the event horizon itself, but rather the black hole's shadow, a zone where light has been so severely bent by gravity that it falls into the black hole rather than escaping. The size and shape of this shadow depend critically on the spacetime geometry around the black hole, which is determined by general relativity. The observed image matches the predictions of general relativity with remarkable precision, providing powerful confirmation that our understanding of how extreme gravity warps spacetime is correct. The time dilation near the event horizon has implications that extend beyond just clocks running at different rates. It affects the very concept of simultaneity. Events that are simultaneous for an observer hovering far from a black hole are not simultaneous for an observer near the event horizon. Consider two events happening at the same moment according to a distant observer's clock, one event occurring near Earth and another occurring near a black hole. An observer near the black hole, if they could somehow compare clocks with the distant observer, would measure these events as occurring at different times. Spacetime near a black hole is curved so severely that the usual notions of now and simultaneous break down. There is no universal present moment that extends throughout the universe. Each observer has their own present, defined by their own proper time, and these presents do not necessarily align. This brings us to one of the limits of our current understanding. While we know how time behaves outside and very near the event horizon, our knowledge of what happens at and inside the horizon is less certain. General relativity provides mathematical descriptions of the interior, predicting that an observer who crosses the horizon will inevitably be pulled toward the central singularity, a point where spacetime curvature becomes infinite and our equations break down. However, we cannot directly observe anything that happens inside the event horizon because no information can escape from there. Everything we know about black hole interiors comes from mathematical extrapolation, not from observation or measurement. Furthermore, general relativity itself is likely incomplete at the very extreme conditions near the singularity. General relativity describes gravity as spacetime curvature, treating spacetime as smooth and continuous. But we know from quantum mechanics that at sufficiently small scales, space and time might not be continuous at all but instead made up of discrete, quantized units. At the singularity of a black hole, where all the mass is theoretically compressed into an infinitely small point, quantum effects of gravity would become important. We do not yet have a complete theory of quantum gravity that successfully merges general relativity with quantum mechanics. Therefore, our understanding of what truly happens at the center of a black hole remains speculative. The predictions of infinite curvature and infinite density are signals that our current theory reaches its limit, not necessarily descriptions of physical reality. Similarly, there are questions about what happens during the formation of a black hole. When a massive star collapses, it does so in finite time from the perspective of someone falling inward with the collapsing matter. But from the perspective of external observers, the surface of the collapsing star appears to freeze just as it approaches what would become the event horizon. The formation of the event horizon itself, from the external perspective, takes infinite time. This raises deep questions about whether event horizons have fully formed in the finite age of the universe, or whether what we observe as black holes are objects that are asymptotically approaching becoming black holes but haven't quite finished the process yet. Most physicists believe that for practical purposes, these distinctions don't matter. The objects we call black holes behave in every observable way as if they have event horizons, and the differences between a fully formed horizon and one that is infinitesimally close to forming would be unmeasurably small. Another area where our understanding is incomplete involves the interplay between quantum mechanics and black hole horizons. In the 1970s, Stephen Hawking discovered through theoretical calculations that quantum effects near the event horizon should cause black holes to emit radiation, now called Hawking radiation. According to quantum field theory, empty space is not truly empty but filled with quantum fluctuations, brief appearances of particle-antiparticle pairs that emerge from the vacuum and quickly annihilate. Near a black hole's event horizon, it's possible for one particle of such a pair to fall into the black hole while the other escapes. To a distant observer, it appears that the black hole is emitting particles. This process causes the black hole to very slowly lose mass over time, eventually evaporating completely. However, Hawking radiation has never been observed directly because it is extraordinarily weak. For a solar mass black hole, the radiation would have a temperature of only about 1/10,000,000th of a degree above absolute zero, far too cold to detect against the background radiation of the universe. Only very small black holes, far smaller than any we know of, would emit enough Hawking radiation to be detectable. So while we have strong theoretical reasons to believe Hawking radiation exists, it remains an unconfirmed prediction. The existence of Hawking radiation also raises a famous puzzle called the black hole information paradox. According to quantum mechanics, information about the physical state of a system cannot be destroyed. But if something falls into a black hole and the black hole later evaporates completely via Hawking radiation, what happens to the information about what fell in? Does it disappear, violating quantum mechanics? Is it somehow encoded in the Hawking radiation? The resolution to this paradox remains debated and is connected to the search for a complete theory of quantum gravity. For our purposes, what matters is recognizing the boundaries of confirmed knowledge. Time dilation near black holes is firmly established by theory, experiment, and observation. Hawking radiation and the ultimate fate of black hole interiors remain active areas of research where predictions exist but direct confirmation does not. Returning to what we do know with certainty, the gravitational time dilation near black holes represents one of the most extreme environments in the accessible universe. No known physical process produces stronger gravitational fields in a stable configuration. Neutron stars, the collapsed cores of stars not quite massive enough to form black holes, produce extremely strong gravity. But even at the surface of a neutron star, time dilation is measurable but not infinite. Only at the event horizon of a black hole does time dilation reach its ultimate extreme, approaching infinite slowing from the perspective of distant observers. This extreme time dilation has occasionally led to imaginative speculation about using black holes for time travel. The reasoning goes that if you could somehow survive orbiting very close to a black hole for a brief period, then return to distant space, you would find that much more time had passed elsewhere. In principle, this is correct. You would have effectively traveled into the future of the external universe. However, the practical obstacles are insurmountable with any conceivable technology. To hover at a fixed position near a black hole requires enormous energy to counteract the gravitational pull. The tidal forces, the difference in gravitational pull between your head and feet, would be lethal long before you got close enough for dramatic time dilation. For a solar mass black hole, these tidal forces are extreme even far from the horizon. Only near supermassive black holes, millions or billions of solar masses, would the tidal forces at the event horizon be weak enough for a human to potentially survive crossing, and even then, you could never communicate what you experience to the outside universe because no signal can escape from within the horizon. What makes gravitational time dilation near black holes so scientifically important is not speculation about time travel, but what it reveals about the fundamental nature of time itself. Before Einstein, time was considered a stage on which events occurred, universal and unchanging. General relativity revealed that time is part of the structure of the universe, woven together with space into a four-dimensional fabric that can be stretched, compressed, and curved by the presence of mass and energy. Time is not absolute. It is relative, flowing at different rates for different observers depending on their motion and their position within gravitational fields. The fact that we can measure these differences, from the tiny effects in GPS satellites to the extreme dilation predicted near black holes, demonstrates that this is not abstract philosophy but concrete physics. The universe does not operate according to our intuitive expectations. Time genuinely passes at different rates in different circumstances. A clock deep in a gravitational well runs slower than an identical clock far from gravity, measured in elapsed ticks. This is as real as the fact that water flows downhill, or that planets orbit stars. The verification of gravitational time dilation stands as one of the great triumphs of theoretical physics. Einstein predicted this effect from pure mathematical reasoning, working out the consequences of his insight that gravity is spacetime curvature. Decades later, technology advanced sufficiently to test the prediction, and nature confirmed it in precise detail. Every subsequent experiment and observation has reinforced this confirmation. The corrections applied to GPS satellites work. The gravitational redshift observed from white dwarf stars and neutron stars matches predictions. The timing of signals from pulsars in orbit around each other shows exactly the time dilation effects general relativity predicts for their orbital motions. The shadow of the M87 black hole appears exactly as the theory says it should. At every scale we can test, from laboratory experiments to cosmic observations, gravitational time dilation behaves exactly as general relativity describes. Yet even as we celebrate these confirmations, we must acknowledge the limits. We cannot place a clock at the event horizon of a black hole and read it. We cannot send a probe into a black hole and receive data back about conditions inside. We cannot test quantum gravity effects where spacetime curvature becomes extreme at microscopic scales. Our knowledge is constrained by what we can observe and measure. The behavior of time as it approaches the event horizon, as viewed from outside, is well understood and verified. The behavior at the horizon and beyond enters the realm of mathematical extrapolation where our theories may need modification once quantum effects are properly incorporated. This is not a weakness of science but a strength. Science distinguishes carefully between what is known, what is strongly inferred, and what remains uncertain. Gravitational time dilation as measured in laboratories, in orbit, and through astronomical observations is known with high confidence. The existence of event horizons is strongly inferred from observations of objects that behave exactly as black holes should, showing the predicted effects on light and matter around them. The detailed physics at the singularity remains uncertain, awaiting a theory that successfully unifies gravity and quantum mechanics. Understanding how time slows near black holes requires accepting that the universe is strange in ways that defy everyday intuition. Time is not what it appears to be. It is not a universal metronome ticking away uniformly throughout space. It is a dimension, interwoven with space, responsive to the presence of matter and energy, flexible and variable. An hour near a black hole is not the same as an hour far from a black hole when compared by different observers. Both measurements are correct within their own frames of reference, yet they disagree. This is reality. This is how the universe actually works. The implications extend beyond black holes. Any gravitational field produces time dilation, however small. Time on Earth's surface runs slightly slower than time in orbit. Time at sea level runs slightly slower than time on a mountain peak. Time near the sun runs slower than time in interstellar space. These effects are tiny in everyday circumstances, measured in billionths of a second over years. But they are real, measurable, and must be accounted for whenever precision timing matters. The universe is not arranged in neat, absolute reference frames where everyone agrees on what time it is. Instead, we inhabit a cosmos where space and time are relative quantities, where measurements depend on the measurer's circumstances, and where extreme environments like those near black holes reveal these relativistic effects at their most dramatic. As we conclude this exploration, reflect on what we've discovered. We began with the historical assumption that time flows uniformly throughout the universe. We found through experiment that this assumption is false. Gravity affects time, slowing its passage in strong fields relative to weak ones. Near black holes, where gravity reaches its maximum intensity, time dilation becomes extreme, approaching infinite slowing at the event horizon from the perspective of distant observers. These are not speculations but confirmed properties of nature, verified through precise measurements and astronomical observations. The mathematics of general relativity describes these effects with extraordinary accuracy, matching every test we've been able to perform. Yet we also acknowledge the boundaries of knowledge. The interior of black holes remains hidden behind event horizons that permit no information to escape. The point of infinite curvature at the singularity likely signals not a physical reality, but the limit of general relativity, a place where quantum gravity effects that we don't yet fully understand become crucial. Science progresses by pushing against these boundaries, designing new experiments, making new observations, developing new theories that might extend our understanding into currently inaccessible regimes. What remains certain is this: time near black holes slows dramatically compared to time far away. This is not theory awaiting confirmation but established physics, as solid as any knowledge we possess about the universe. When you look up at the night sky and consider that there are supermassive black holes at the centers of most galaxies, including our own, you are looking at regions of spacetime where the fabric of reality is stretched and warped, where time itself becomes something profoundly different from our everyday experience. And we know this not through guesswork or imagination, but through careful reasoning, precise mathematics, and detailed measurements that confirm predictions made a century ago by a physicist who dared to reimagine what time could be. If you found this journey through gravity and time worthwhile, consider liking this video and subscribing to the channel for more explorations of how the universe actually works, one verified fact at a time. Thank you for listening, and may your own time, however it flows, be spent in curiosity and wonder.